In this lesson, I'm going to show you how to interpret a simple harmonic motion graph. Simple harmonic motion includes light and sound also. So the first thing I want to point out is that all periodic motion can be described by this formula. V is equal to the product of the wavelength and the frequency of the wave. We can, of course, rewrite this as lambda divided by the period because frequency is equal to 1 over period. This graph, we have what looks like a distance here, so that would be, this would represent the amplitude versus x, and x would represent multiples of the wavelength. So this would be wavelength. And I say multiples of a wavelength because we have to identify one complete wave. So I'm going to pick this point to this point. Right here we have one complete wave right there. So the wavelength here is going to be equal to, it looks like it goes from 5 to 17. Wavelength is 17 minus 5, or 12 meters. That is the wavelength of this particular wave. We see that we're also given the speed of the wave. Speed of wave is given as 24 meters per second. So we can now use this formula V is equal to lambda F to calculate the frequency. So V is equal to lambda times F. V is 24 meters per second. Lambda is 12 meters and times F. So meters will cancel, and 24 divided by 12 tells us that the frequency is going to be equal to 2 cycles per second. And sometimes that's written as just 2 s to the negative 1, meaning 2 something per second, and the something would be whatever is oscillating. In general, we just say cycles, 2 cycles per second, or we just convert that to 2 hertz. Okay, and that's the most common unit, hertz. Now, let's take this opportunity to figure out what the period is. Since F is equal to 1 over T, what that means is that T is equal to 1 over F, or 1 over 2, and that's 0.5 seconds. So the period of time for one complete cycle is going to be equal to 0.5 seconds. Here's another graph. We're going to do the same thing here. However, when we look at this, this is displacement versus time. So the displacement, again, we have A right here. And it looks like A, I'm going to write that down. A is equal to 90 millimeters. But I want to point out that that is not lambda. A is not lambda. It's not the same thing. That's the amplitude. So let's pick a wave here. Now, what I could do is I could start along the x-axis and go like here, but I don't like this number because this is like 25 and 50, and this starts between 25 and 50. It's not nice round numbers. The easiest thing would be just start at one extreme, the top of the wave, and go to the next time we're at the top of the wave like that. That's one complete cycle. Or I can start here at the bottom of the wave and go up and come down. That's another complete cycle. It doesn't really matter where I start, just as long as I make a note of a complete cycle. So this is from 0 to 50. So 0 to 50, that would represent, what would that represent? It would represent our time. So our time, which would be time of one cycle, is period. T is going to be equal to 50, and I'm not sure what those units are. Let's assume that that is a second. Okay, 50 seconds. Now, that means that our frequency is equal to 1 over 50, which is 0.02 hertz. There you go. So I know what the frequency is. I don't know what the lambda is, and I don't know, therefore, what the velocity is. So there's not much more that I can do with this graph. I cannot calculate anything. So both are unknown, okay, by this graph as depicted. by graph. So the information is actually incomplete here. It would be useful to know what the wavelength is or what the speed is, like the previous graph showed us. We were told that the speed is this, so therefore we can determine the third out of the three variables.